Visualization of results is a great way to understand what's going on with a model, as well as communicate technical information to a non-technical audience. Join me today as we learn how to use Matplotlib to visualize classification boundaries. Welcome, I'm Gregory Tarpon with GNT Learning, and on this episode I'm going to help you learn how to visualize classification results using Matplotlib. Now Matplotlib is great for making scatter plots, histograms, and lots of other simple figures, but it's not so obvious how you're going to use this tool to visualize classification results. Now we're not going to do a deep dive into Matplotlib today. Instead, we're going to focus on this one very commonly asked question of how do I visualize these results, and hopefully we'll gain some intuition along the way about how to use this tool in non-obvious ways. We start with our usual imports of Numpy, Pandas, and Matplotlib. As always, we're going to need some data to work with, and today we're going to use some information from the annual World Happiness dataset. Specifically, we're going to take data from 2016. Now, this World Happiness dataset contains information with a lot of different descriptors about countries, somewhat related to happiness and other just metrics in general. We can go ahead and see here from df.info all the information available in this dataset. So we see we have, in addition to country, we have information about happiness, economic information, information about life expectancy, etc. And we're going to be interested in today is looking at the regions of the different countries and how we can classify these countries based on this other information. Now, the first thing we're going to do is look a little bit at basic Matplotlib behavior. To that end, we're going to start with just the simplest kind of plot we can make, which is a scatter plot. Scatter plots take two arguments, and we're going to get those arguments by grabbing individual columns from our data frame. The two we're going to look at initially here is the economy, which is actually the GDP per capita. And we're going to look at the other column of happiness score. And they will give us the X and Y values on a nice little scatter plot. We could then add some additional details here. We'll talk about that in a bit in terms of axis labeling, etc. The main thing that is important here is that PLT scatter gives us a very great way to just glance at the data and kind of see what's happening in terms of the raw information. So without any real analysis here, we can see that, having a stronger GDP per capita correlates with a higher happiness in the country. Likewise, we can use this exact same structure here to make another quick check. In this case, we're going to see, instead of the economy and how it affects happiness, how health, or specifically life expectancy, is influencing happiness. Expectancy. We run that, and we see we get another similar scatter plot, again with a positive correlation. Now, you could spend a lot of time in your EDA or exploratory data analysis building little plots like this, comparing variables, and getting sort of a baseline idea of how things work. And what makes this a nice data set today is we can see that they have a complete data set that has lots of information in it, and it gives us these pretty easily interpretable connections between these different variables. Now, what we're going to do is turn to a classification problem. So these two variables, or all the variables rather in these plots, are continuous variables. So we need something discrete if we're going to do a classification, which is why we're going to use the region for these different countries. So to see what that actually looks like, let's go ahead and do df region and look at the value counts. We run that, and we can see these countries are broken up into a number of different subregions. Some of them have a lot of countries in them, Sub-Saharan Africa, for example, and some of them are pretty specific categories, Australia and New Zealand, of course there is too. Now, from a broader perspective, we could question why the countries are broken up in these specific regions. We could change it to doing something like per continent or something else. But for the day, we're just going to stick with the data set we're given and assume that these regions are well-defined, well-thought-out regional choices. And so we're going to try to classify the different countries into regions based on the other information we have. Just to get an idea of how this other information above connects to region, let's start with something relatively simple. Let's just color the points from one of those scatter plots with information about the region. Now, while happiness score itself is a somewhat interesting metric, what we're going to actually use today is the other two more clearly defined metrics for our plotting. So first I'm going to do a copy paste here to grab the basic syntax. And then I'm going to go ahead and come back up here and make my life a little easier. And so I don't have to worry as much about typos. It's always a good idea to do copy and paste whenever possible to reduce the amount of little mistakes you make along the way. So now we're making a scatter plot with these two variables. If we look at it directly, another scatter plot, nothing too surprising there. Now, the option inside of scatter to do coloring is to say C equals and give it something to color by. In this case, we're going to color by region. And we're going to see is that this naive choice of simply just taking the name of the region in directly is not going to work. This is the first little place where it gets a little into the details and a little annoying sometimes to use Matplotlib. If we come down here, we basically see that the ultimate error here is that the labels we're given, like Western Europe, are not actually colors, so it doesn't know how to handle that. And there really are a couple ways you can solve this. Option one is that you could just create a new column in your data frame of colors. So you could build a little dictionary, use the .map to go ahead and convert Western Europe to red, Australia and New Zealand to blue, and whatever you want, and explicitly set all the colors, and then just use that column of colors. That is a bit tedious, but is something you can do. And that's more about data frame manipulation than it is about Matplotlib. The other option, the one we're going to go with today, is we're going to instead just use numbers to fill it in. So now we're just going to say, okay, if we can just map all of our different regions into numbers, and those numbers can then be used to color everything. And this is a more typical route because this is the kind of thing that you're going to want to do when you have an arbitrary number of categories. You're going to want to use some sort of encoding to automatically number things. So at that end, we're going to have to insert another cell above this, and we're going to have to define some encoding. Now, there are more manual ways of doing this, but in order to do that today, I'm actually going to use the region or create an encoder using the label encoder from sklearn. Now, this choice is being made mainly because it's just good to be in the habit of using the sklearn's basic tools to do a lot of things for you and to be comfortable with using encoders more generally. So the way you use the encoder is you define an instance of the encoder. We're going to have to go do an import in a moment. Then we can go ahead and take this encoder and fit it, and in this case transform it as well in one step based on the information from some source, in this case our column of region information. What this is going to give us then is something that converts all of these different named regions into numbers 0, 1, 2, 3, etc. And importantly, will leave behind for us this region encoder that we can use to keep track of what numbers correspond to what labels. So, and of course we have to import this for this to actually work. We are going to do from sklearn dot preprocessing. We're going to import our label encoder. As always, make sure to actually run an import if you go back and put one at the top. We can come back down, run our little piece of code here. Our regions are defined. And we can now use these regions instead to color our image. Great. So first pass, we now have a scatter plot where we've colored all the points by the category they contain. That's a nice start, but not really what our ultimate goal is. What we really want is to know what is the predicted category for all these other regions out here. What if you have this particular combination of life expectancy and GDP, what region do you expect the country is part of? Well, that means building a model. So before we can plot anything, we need to actually have a model that makes that prediction. So today what we're going to do is we're going to make basically the most naive, sort of simplistic model possible here. We're going to have two inputs, which are going to be our health and life expectancy. And again, as always, it's a great idea to copy and paste to minimize the amount of typos you make. And this is going to be the two pieces of information we want to use. Now, note here, for those less familiar with data frames, that here I was grabbing a single column, so I used to use data frame or df and open square brackets. Here I'm giving it a list of columns. So this inner set of square brackets is because I'm giving it multiple things at one time. So the exercise model, or the independent variables for my model, are going to be the life expectancy and the GDP. We already know the output of our model is going to be the regions these things belong to. So we need to build some sort of model, and we're going to build basically the simplest model possible, which is going to be a k nearest neighbor model. And again, we're going to lean on the convenience that is sklearn for implementation here. All right. And the way we're going to build the model is we're going to have set it to 3 nearest neighbors. So for every single point that we're interested in, if you look at the 3 nearest neighbors, what region they belong to is going to determine what our model makes as its prediction. Now, this is not a well thought out choice. This is just an arbitrary choice of variable today for making a plot. And it's something you could play with afterwards if you want to see some interesting differences and visualize how this behaves. Okay. So let me go ahead and fit our data, where X is our input, regions is what we're trying to predict. And then just, for example, we can do knn.predict to see how this is going to look. And of course, we did need to import something from sklearn as well. So from sklearn neighbors, we're going to import our kneighbors classifier. I want to make sure to run that. Just because I want to be paranoid about typos, I'm going to copy that name and make sure that I absolutely have it typed correctly down here. We go ahead and run that, and we see this is the prediction our model makes. Well, as we said before, we replaced the regions from their names back to some numeric encoding, 0 to, in this case, 9. And so our predictions are, of course, going to be values 0 to 9. So visually, it doesn't look like much here. And this is why we need to have these plots. Well, we need to have some way of representing this information that's more useful. Okay, well, the first thing we can do is we can say, okay, we're making predictions based on all of this data. So let's come up here and let's, instead of coloring things by region, let's go ahead and make a plot where we color these things by the prediction. So let's come here, say knn.predict x, run the code, and now we see what our predicted region is based on the model. And, well, again, this is somewhat of an underwhelming result. Okay, we're coloring individual points. We're not talking about what's happening more broadly. And sure, this is our prediction, but it's really not going to be that different than the actual raw data for the true values. The only real difference is going to be that countries that are a little bit out of place compared to other ones in their region are going to be colored based on what's around them. So this is some ways just a smooth version of what we have above. Before I move into the details here, there's two caveats I want to bring up. One is that when we're doing this operations, or these operations, we made sure we have this X and we have this Y, and these came from a data frame. So by construction, they have the same number of points in them, and that's absolutely required for this calculator to work. The same thing is required of the color. You have to have as many entries as you have data points for this to work. When you're using the regions directly or a column from the data frame, there's no problem there. But the more you get into doing additional work and effort with building a model, designing things like that, it's easy enough to get a little bit off what you're doing. One of the things we didn't do in this model was a proper test train split. And that was somewhat because we're just trying to make a quick model to have something here. But a secondary, smaller reason for that is if we did do a test train split, it wouldn't actually be very easy to visualize in this case because we still need to have a prediction for every single point. We could get into a conversation there about, well, okay, you build a model on one set of data and then you show the predictions on the other set of data, but I didn't want to get too bogged down in those details today because we're trying to get the mechanics of making these nice plots. Now, with that said, we still need to make a nicer plot. We still need to know what happens in general for an arbitrary point and visualize that somehow. So we have our model in hand, but what we need now is to make a prediction at every single point in this figure. To that end, we need to generate every single point in this figure. So the first step to that is actually to turn to a little bit simpler problem, which is that of calculating every single value across some range. And to that end, we can use Numpy's linspace. So Numpy's linspace, if you just run it with some example, is it gives you all the values from 0 to 1, in this case, 0 to 1, and it gives you 101 points for that. So this is a great way in one dimension to describe every possible value. We have a figure, we need to do the same thing in 2 dimensions. So how do we get all combinations of points in this plot in order to do calculations on them? And this is where we turn to np.meshgrid. Now np.meshgrid is something that can be pretty confusing to use and is really the motivation behind this entire presentation today. So we'll start off with something relatively simple. Let's do a meshgrid where we give 2 arguments. One is the range 3, so i.e. the value is 0, 1, 2, and the range 4, i.e. the value is 0, 1, 2, 3. And let's just look at what the meshgrid does. So the meshgrid gives us this slightly ill-formatted set of values. And it really consists of 2 things. We saw that we gave it a range of 3 and 4, and so our output are these 3 by 4 blocks of numbers. The first block of numbers, or first array of numbers, is 0, 1, 2 in the rows repeated, and the second block is 0, 1, 2, 3 in the columns repeated. So between those, we do actually have a description of all the coordinates, but it's not formatted in the way that is most natural for giving it to a model to make predictions. So conceptually, what we want to do with these points is rearrange them into something that looks like the X data we were working on before, so we can feed it into the model. So let's step back for a second and see what that X data actually looked like. So in this case, because it came from a data frame, it still is a nicely formatted data frame. So if we go ahead and just put a .values here, we can see that it actually consists of this long list of pairs of values. So it's a 2D array where the 0th dimension corresponds to just the different points of interest, and the first dimension corresponds to the different columns we took from the original data frame. Okay? So we want to use meshgrid to generate something that looks like this. Keeping that in the back of your mind, we can look at how we can start to break down this meshgrid. Now, a very common thing you'll see people do with meshgrid is take and split it into the two separate arrays. Let's go ahead and copy that. And then go ahead and glue them back together individually. So this could look like something where you, for example, flatten each array, shape -1, y dot, rather reshape -1. Right? And kind of look at them side by side. So this gives you something that looks like the sets of points, except what we actually have is two separate one-dimensional arrays. And then we need to glue them together. For those more familiar with some of the nice features built into Python, zip will basically allow you to take an arbitrary number of one-dimensional objects and zip them together by the different entries, basically iterate over multiple things simultaneously. And as a nice little trick, you can get something like this. That'll give you a list of the points you can use. And this is a pretty effective way to do it, and you'll see a lot of variations on this. Often enough, you'll see people do this kind of thing in a loop or in several more steps, but the core concept is basically the same. Of they split the mesh grid into two pieces, and they go ahead and figure out how to iterate through them in a way that allows you to put all the combinations together. So in this case, we can see we got 0, 0, 1, 0, 2, 0, and then we have 0, 1, 1, 1, 2, 1. And by doing this, we go through all combinations of 0, 1, 2 with 0, 1, 2, 3, and have all the values we could possibly be interested in. Now, for those that are a little more familiar with Numpy, this is a pretty unsatisfying answer, because what Numpy does at its core is allow you to do lots of rearrangements and manipulations of high-dimensional objects. So going back to low-level Python tools like zip is a pretty inefficient method. It's not really a problem for the most part, but it isn't the most natural way to use Numpy, though it is the very common one you will see. An alternative here is instead to build this up piecemeal, not from the splitting this into two parts, but instead by gluing everything together from the beginning and doing Numpy transformations. Now this looks like first taking this list of two Numpy arrays and actually putting together into a single proper Numpy array. So np.asArray will do that. If you just run this, we can see that we now have a three-dimensional array with all the same information. We then need to permute it to get the order of the different axes correct. In this case, it turns out the most plain choice of permutation, just transposing it, is actually the correct one. So if you run this, we now have something that looks basically correct. 0, 1, 0, 0, 0, 1, 0, 2, etc. 1, 0, 1, 1, 1, 2, etc. And then we just need to get rid of this extra dimension, because we don't need to have this into three separate blocks. And that's a matter of simply doing a reshape, in this case of 3 times 4, comma 2. And where these numbers are coming from, this 3, 4, and this 2, is 3 was the dimension of this, 4 was the dimension of this, and 2 was the fact that we had two different blocks at x, x, y, y before. So that's always going to be a 2. And we just need to keep that 2 separate, but we want to flatten out this other dimension. So we can just multiply those sizes in our reshape. And when we do that, we get something that is actually a proper Numpy array rather than a list of tuples. Now, all of this is just various ways of playing around with meshgrid. And it really doesn't matter how you get to the final answer. The core idea, though, is to get the meshgrid and begin transforming it by whatever set of tools makes the most sense to you until you can get it into this sort of a structure. Having seen it once, as in this example, you could copy this exact code, either the version here I'm showing with Numpy or something that's a little more in the style of plain Python. For our actual problem today, I'm going to go ahead and take this version, and then we're going to put our pieces together and see what we can do. Now, one additional advantage of meshgrid that's important here is that I don't have to specify integer values. I can give this a list or iterable object containing anything, and it'll give me all the combinations for it, which means I can get the right values for x and y over some arbitrary range. In this case, I'm going to use that linspace for the 1D and say, well, I want values from 0 to 1, I want 100 of them, and for my y values, I want to have values from 0 to 1.85, and I want 100 of those as well. And for those who are curious, those values are coming from this plot above here. So values range from basically 0 to 1 and 0 to about 1.85. Right? So we can specify we want to go over those complete ranges. We can do x values here, y values here, and we need to make sure that we use the right number of points for flattening this. Now, in general, I said this is required to be the right size to flatten the shape you have based on the number of points. However, we're making a two-dimensional object here. Our second value is always going to be 2. So we can just use a value of -1 here. And Numpy is smart enough to recognize that it's going to be 2 and whatever makes 2 work. So that'll always give you the right number of points. And then we'll go ahead and save this to a variable and see what we have here. All right. Now, it's a little bit too long to put the whole thing on screen at once, but we can see, okay, we're getting something 0, going through some values, 1, going through some values, and the endpoints look right, and we can see that we are getting the overall right behavior. All right. Let's take one moment here to just sort of clean this stuff up a little bit, comment out some things that we're not going to really need to look at again. And we're going to go ahead and do a kernel restart and run all. Great. Now we have some points of interest that we can use with our model. So before, in our model, we had knn.predictivex allowed us to make predictions on all of the actual data we were training on. Now we can go ahead and use this prediction to ask for what the prediction is at every single possible coordinate that could be in the plot. And this is, of course, a gigantic 1D array of answers that is completely impractical to look at manually, which is why we turn to plotting. Let's start off with looking at how we can build a nice little scatter plot using these coordinates we just generated. So this set of coordinates shown here is a 2D array, and this 2D array has effectively 2 columns of information. One is the values we want to use our x coordinates, and one is values we want to use our y coordinates. So if we're going to do a scatter plot on these points, we simply need to say we want to use that I'll use for all rows, and then that 0th column for the x-coordinates. And we want to use the values at all rows and this 1th column, if you will, for the y values. And then we need to do something with that. If I just plot this, it'll be a giant blue rectangle. So just to demonstrate that we can set something arbitrary here, we can say np.random.choice and use this to make a set of random values and color them in. And the last piece here I want to include is this alpha equals 0.1. So if you go ahead and run this, what we get is a randomly colored rectangle of values. So what we're showing here is that we can take the coordinates given some arbitrary set of information and plot whatever we want. Now there's a little detail I want to mention here. The way we're plotting this is we're saying we're going to taking 100 points by 100 points and putting it into this area. We're not doing anything that's actually continuous in space. It just has the illusion of being continuous because there's lots of little points. This means that if you want to have a much larger image, if you do things to resize your figure, you may have to use more points. Or if you're using something that's very small, you can use potentially fewer points. It also means you have to worry a little bit about how things are actually colored, which is where this alpha of 0.1 comes in. What the 0.1 alpha says is instead of drawing a dot of the full color, it makes it 90% see-through and 10% that color. And that's important when you're going to have lots of points that are effectively little overlapping dots. So it looks like something that's a relatively smooth gradient range of colors rather than just discrete points kind of spattered all over each other. So now that we see how this looks in general, we can go ahead and put in our actual predictions and see what it looks like. We run that, and we actually realized I failed to copy and paste that, so we actually had the older paste there. So chords, we can actually paste the thing we want. And now we have a colored background where the colors match with the different categories to show what our predictions are. So we have one category down here, another one up here, and you can see because we have 10 different categories, this is a pretty complicated looking thing, but it's still relatively easy to see. Now, you will, in a lot of your problems, have much simpler ones that have 2 or 3 categories, and you'll tend to get much more simple shapes than this. This is kind of at the extreme edge of what is kind of feasible to show here. Well, we've created our background of predictions. Now it'd be nice to overlay this with the actual points we have. So we come back up here and grab our actual data points that have been colored appropriately. We can now overlay them. And we're just going to go ahead and do another kernel restart and run all to clean things up a little bit. All right. And now what we see is we have both the actual data points in nice, solid, relatively dark colors, and we see the background is the predictions for the different regions. And in fact, here we actually probably don't want to use the predictions. It would probably be better if we actually use the original values. So let's go ahead and just fix that. And now we can see some of the discrepancies as well. So you can see, for example, there's a light green point here, but that's not what the prediction in that region is. Likewise, we have the dark blue down here in the middle of this light green region. Now, there's a couple other things we'd like to do here to make this a little bit more presentable as a plot. We physically sat here, we know what all these points mean, all these colors mean, but it's not completely intuitive to someone else. First thing we want to do is clean up the colors a little bit. They kind of run together. So one of the features, in addition to using C to note the color, is you can also use CMap to denote what the sets of colors to use are. So in our case, the regions were 0 through 9, and those were being automatically assigned to colors. This CMap argument can be used to set a blue to red range, black to white range, or one of any number of different ways of doing it. The ones that are particularly useful for these categorical ones are these tab ones. There's a tab 10, tab 20, and a few others that give you 10 distinct colors to use for doing this kind of thing. And we need to make sure to go ahead and include this option in both of our figures here. Now we run that. We get something that has a little bit of a brighter set of colors, and it's a little more distinct. It's a little easier to see, oh, this red point totally does not belong to this green region. We can also pick out a few little artifacts from our model itself. So you can see right here, for example, there's this like slightly reddish splotch that was completely not noticeable before. And what this reddish splotch is actually an artifact of using a 3 nearest neighbor model, where the 3 nearest neighbors were this red point, one green point, and some other point, such that it actually didn't use the green background as the default. It is predicting some other classification. Same thing's happening over here. And so those little details are a lot more visible when you have a good set of colors to look at. In this case would be an indication that if I were to be serious about this model and presenting it, maybe a 3 nearest neighbor is not going to be good from a visualizations perspective, and also indeed may have just some kind of strange artifacts in it. Now, the next thing we'd like to have here is some actual labeling for all these colors are. There's way too many. We need to understand what's going on here. Now, there is an option to make a legend, and that's a different route to go down. The one I'm going to propose and recommend for people when they're doing this background coloring for a classification system is to actually use the built-in color bar. Now, the color bar can be a little bit finicky to use. So rather than go through the details and say, oh, you can try this and that, you get lots of interesting error messages, let's just go through what the kind of correct answers are for this. So the color bar is going to take 2 arguments. The first one is going to be just a set of numbers for what are the different values you're using, 0, 1, 2, 3, 4 in our case. So we can easily just get this by using the region encoder.classes. Now, region encoder.classes is the information about what all of the different classes in our system was. As I mentioned before, in the encoder itself, please scroll back up to that for just a moment. In the encoder itself, we're going to map these names to numbers, but the encoder remains, and it knows and remembers what that connection is. So we're going to be using that to help build our labeling down here. For this first part, we just need to know how many classes there are. So we just need to get the length of that and use that as a range to say how many different ticks or how many different colors are going to be labeled on our color bar. The second part is this sort of strange little thing called a formatter that is part of Matplotlib. Now, in of itself, it's something that I would say is more advanced in trying to figure out and get used to. And unless you're going to get really into the nuts and bolts of how Matplotlib works, it's generally not going to be worth trying to figure out as someone who is occasionally making interesting plots. Though I do recommend fixing your typos. So the way this formatter works is it's a special sort of function that exists, or rather class that exists, that defines the connections between how to do a lookup for the values. The nuts and bolts here are just that it wraps a function, and that function knows how to take information to figure out what label to use. And the information we need is captured inside that list of classes inside the region encoder. Right. So in a nutshell, there's a lambda function being defined, which is taking in two arguments. The one that's important is the value we're looking at, 0, 1, 2, 3, 4. That information is being used to look at the list of classes inside our region encoder and grab the correct name. And then this function formatter is wrapping that function inside this Matplotlib custom object. And that's the exact format that is required by this color bar. Now, there's a lot of details there to get kind of caught up in. My major recommendation here is not to get caught up in those details, and instead just to kind of accept this is the format you're going to have to use if you want to use the color bar. The alternative to this is to do the legend, which is going to be a very different way of handling how to do the scatter plot here. And both of these things kind of highlight sort of the limitations on using Matplotlib to make really fancy plots easily. But it's not too bad to do it for this specific case. All right. So now what we have is essentially the same plot as we had before, and we have colored names, or labeled colors for all of the different things we're using. So this looks pretty good on the whole. We have one last little thing we'd really like to have here, which is some axis labels. We've been kind of putting this off for a while, and we're going to go ahead and get them now. So our x-axis is health, life expectancy. I'm just going to call it life expectancy. And our y label, plt.y label, is going to be our GDP per capita. And we can go ahead and run this, and it'll add the labels if I don't make any typos. And so there we have it, a way to do a visualization of a classification problem with a large number of classifications, and to clearly see what regions of a domain correspond to different inputs. Now, there's a lot of little things that can be done to kind of expand upon this. The example we showed here, we built a model around having two inputs, which were exactly the two inputs in our plot, the health and economic indicators from this data set. And that was very convenient to have exactly two things in our model and exactly two things we can show in a two-dimensional plot. If you're building a model that has more inputs than two, and you want to make a plot like this, you're going to have to choose some value or values to fill in the rest of the inputs for your model. So usually you can just choose a typical average value for everything else and make this plot. Or in theory, you can make multiple plots. If you had only 3 variables, for example, you could make multiple plots like this for a low value, a middle value, and a high value, and show how this background color changes and changes the predictions you make. Whatever your solution, though, is, you do eventually run into the problem that you're just having a high-dimensional system you're trying to represent with a 2-dimensional image. That's more of a limitation on just dimensionality of the problem, and not something you can really get around in terms of visualization. Your visualization for something like this is just inherently going to be 2-dimensional. The next thing we kind of talked about here is the limits of Matplotlib. So Matplotlib has some really great basic functionality for getting a plot together very quickly. So scatter plots, histograms, etc. That you just out of the box you can make them work. And as we showed today, you can actually get some a little bit more sophisticated things out of them. For example, having two scatter plots overlap, where one is a background for your prediction and one is a foreground of your actual values that are measured or known, you can build something relatively sophisticated using this pretty simple tool. And you only had to take advantage of 2 or 3 basic arguments to this beyond the coordinates themselves, which were the color, alpha, and CMAP. Now, that said, Matplotlib does have the functionality to build much more complicated things, and we saw a little bit of that with color bar, and we also saw how that starts to turn into something very complicated, very specific, very quickly. So this is really at the limit where I would recommend people actually use Matplotlib. There are other packages for doing plotting when you want to get into the sophisticated things that are often better to use, and those are Bouquet and Seaborn. Bouquet is really good for handling very large amounts of data and building sort of custom visualizations, something like this. Seaborn is really best known for its ability to make multiple plots simultaneously. So if you have something like a data frame and you want to make histograms of all of the different columns, or you want to look at the correlation scatter plots of every pair of variables, Seaborn does that in very few lines of code and allows you to mass produce relatively good looking plots pretty quickly. So both of those are very popular tools depending on what you're doing. Another comment that's important to make is we looked a lot today at using meshgrid. And meshgrid is super powerful, but it has the downside that it's a little bit confusing, especially for people who are new to data science. And so a lot of times you'll get a script from somebody that will use meshgrid to do plotting and do something like this for you, and it won't work. And the problem with that is not that they're using meshgrid incorrectly, but they're giving you a function that they expect a very specific setup to work. And if it doesn't work, it's very painful to debug exactly how they're using meshgrid, exactly how they want your inputs to be formatted to unwrap everything correctly. And a lot of times it's going to be easier to just write it yourself from scratch than it is going to be to debug the helper function that was nicely provided for you. So with that, you now know how to make some very stunning visualizations to help you express your ideas and explore the data a little bit more for yourself. Thanks for watching, and a special thanks to those whose contributions help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.